All right, let's dive right into this explainer. Today, we're unpacking the invisible forces that literally power our modern world. We are exploring a super fundamental observation of physics from Chapter 29, Magnetic Fields Due to Currents. We're going to break down exactly how and why an electrical current produces a magnetic field around itself, and how we can actually use math to predict that behavior. So you probably already know that stationary charges have electric fields around them, right? That's classic electrostatics. But what actually happens when those charges start moving through a wire? Well, suddenly the rules change completely, and we enter the dynamic, frankly, much cooler realm of electromagnetism. A simple electrical current fundamentally alters the space around it, creating this twisting, invisible magnetic force. Today, we're going to scale up our understanding, starting from a tiny theoretical microcurrent all the way up to complex, powerful electromagnets. Here's the roadmap for today's explainer. We'll kick things off with the Biot-Savart law, then look at straight wires and arcs. Next, we'll cover the forces between parallel currents, Ampere's law and symmetry, the mechanics of solenoids and toroids, and finally, we'll view coils as magnetic dipoles. Let's get to it. Starting off with Section 1, the Biot-Savart law. This is the bedrock mathematics that explains the magnetic field produced by a single tiny current element. Think of the Biot-Savart law as the ultimate starting point, the source code of electromagnetism. It tells us that this tiny differential magnetic field, which we call dB, depends on the current, the length of our little wire segment, and the inverse square of the distance from that segment. But here's the real kicker, the cross product. The magnetic field relies entirely on a cross product between the direction of the current and the vector pointing to wherever you're measuring from. Simply put, magnetic fields operate in true 3D space. They act perpendicular to both the current and the distance. Because of this specific geometry, if you stand so that a current flows directly toward you or directly away from you, the magnetic field you observe is literally zero. You only catch that field at its maximum when you're looking at the wire from a perfectly perpendicular angle. Moving right along to Section 2, straight wires and arcs. Now we get to build the geometry and see what happens when we integrate that foundational law along a full physical wire. Just look at this. This brilliantly illustrates our math in the real world. If you run a straight wire carrying a current straight down into a flat surface, and you sprinkle some iron filings around it, those filings physically align into perfect concentric circles. It's an absolutely stunning visual confirmation of the math. And notice how the circular paths get further and further apart as you move away from the center? That's a direct visual of the inverse relationship we just talked about in the Biot-Savart's law. The magnetic field strength drops off significantly the further away you get from the source. Now, to actually map out these invisible vectors yourself, you just need your own hand. Literally. Try the curled straight right hand rule right now. It's a crucial trick to intuitively orient yourself in 3D magnetic space. Just hold up your right hand and point your thumb along an imaginary wire in the exact direction the current is flowing. Then, naturally curl your fingers inward. The way your fingers wrap around that imaginary wire, that maps the exact concentric circular path of the magnetic field lines. It's kind of crazy that we have this remarkably simple biological tool built into us to decode such complex physical directions. But what if the wire isn't straight? Well, if we bend it into a circular arc, the math shifts to focus specifically on the center of that curvature. The magnitude of the magnetic field at that center point depends on the current, the radius of the arc, and crucially, the arc's central angle. And guys, here is a massive insider tip for your calculations. Whenever you run this math, that angle absolutely must be measured in radians, not degrees. Radian measure is tied to the physical arc length, so if you plug in degrees, it's going to throw your entire result way off. All right, Section 3, forces between parallel currents. Let's see what happens when we throw a second parallel wire into the mix and watch them push and pull. Since each wire creates its own magnetic field, they actually exert a physical force on each other. And this is so wonderfully counterintuitive. In basic electrostatics, we're all taught that opposites attract, right? But with parallel electrical currents, sames attract. If you have two long parallel wires, they physically pull together if the currents are flowing in the exact same direction. If the currents clash and flow opposite to each other, the wires actively push apart. It's this awesome chain reaction where wire A creates a magnetic field, wire B sits inside it and feels a force, while at the exact same time, wire A is sitting in the field created by wire B. And listen, this isn't just abstract textbook stuff. This literal magnetic push is exactly what launches projectiles at supersonic speeds in railguns. In a railgun, a massive current vaporizes a conducting fuse, which creates a pocket of conducting gas between two rails. The massive magnetic repulsion between those parallel currents violently forces that gas, and the projectile sitting right in front of it, outward at insane speeds. Even more fundamentally, this physical force is actually how physicists officially define the ampere, our standard SI base unit for current. I mean, think about it. Counting individual electrons flowing through a wire is practically impossible, but measuring the macroscopic physical force pushing two physical wires apart, you can easily do that in a lab. So the ampere is formally standardized completely around this specific magnetic force. Which brings us to Section 4, Ampere's law and symmetry. Because integrating the Biot-Savart law point by point can get incredibly tedious, physics gives us a massive shortcut. Think of Ampere's law as taking a brilliant shortcut through a nasty maze of calculus. Just like Gauss's law simplifies electric fields, Ampere's law is our cheat code for magnetic fields. If our 3D setup has cylindrical or planar symmetry, we don't have to integrate over every tiny wire segment. Instead, we just draw an imaginary, closed Amperian loop. We evaluate the magnetic field around that simple boundary and just set it equal to the net current passing through it. Bam. It lets us completely bypass pages of calculus and instantly find the net magnetic field. Let's put that shortcut to work in Section 5, solenoids and toroids. These are the absolute workhorses, the actual machines of modern electromagnetics. When we coil a wire into a tightly wound helix, a solenoid, something amazing happens geometrically. The magnetic fields of adjacent turns totally cancel each other out on the outside, but they perfectly combine on the inside. This creates a highly uniform, heavily concentrated beam of magnetic energy right straight down the central axis. Now, imagine taking that long solenoid tube and bending it until the ends meet, making a continuous donut or bracelet shape. That gives us a toroid. Inside a toroid, the magnetic field forms perfect concentric circles completely trapped within the hollow tube. This specific ability to endlessly contain a powerful magnetic field within a closed loop, that's the exact same principle they use in massive tokamak fusion reactors to confine superheated plasma. Take a look at this synthesis of the formulas for all the core geometries we've covered today. Notice how elegantly Ampere's law cleans up the math. For the solenoid, the formula drops down to just the permeability constant times the current times the number of turns per unit length. That's it. No messy integrals. The toroid is incredibly clean too, depending simply on the total number of turns and your radius from the center. It's just a beautiful example of how finding the symmetry in a structure allows us to cleanly predict massive physical forces. All right, final stop, Section 6, coils as magnetic dipoles. Let's bring this full circle and look at a single current loop from a distance. When you zoom way out, a single loop of electrical current behaves exactly like a classic bar magnet with a distinct north and south pole. It produces what we call a dipole field. And if you place this loop into an external magnetic field, it'll experience a totally predictable torque. It will physically twist to align itself. This twist is driven by its magnetic dipole moment, which is simply the number of turns times the current times the area of the loop. And this isn't just some mathematical quirk. This predictable, magnetically driven twisting torque is the fundamental mechanical principle behind literally every electric motor on the planet. So, as we wrap up today's explainer, I want you to consider something kind of wild. If a giant macroscopic loop of electrical current generates a dipole field identical to a bar magnet, what does that mean for the fundamental nature of reality? Could the intrinsic, permanent magnetic fields of the tiny spinning electrons inside of you basically be the exact same mechanism, just incredibly tiny loops of moving charge operating on an unimaginable quantum scale? It's a profoundly cool connection between the massive industrial machines we build and the microscopic, subatomic particles we're literally made of. The rules of geometry and charge hold true at every single scale. Keep exploring, keep questioning, and I'll see you in the next explainer.